Well, good afternoon, everyone, and a very, very warm welcome to each of you to our August Bite-Sized Corrosion series, where we're going to be having a look at the impact of contamination of our waters. My name is Vanessa Sealy-Fisher, and it is my great pleasure to host today's session. In each session of Bite-Sized Corrosion, we try to break down a different aspect of corrosion-related information into what we hope are interesting and informative and, shall we say, palatable nuggets, helping to make your own corrosion experience a little easier to digest. Now, we hope that you'll leave us having learned something new and eager to continue your journey in discovering and understanding corrosion a little more. Now, today we're starting a 6-session mini-series where we look at the contamination of water and the impact of that on the corrosion associated with water. Now, if you cast your mind back to our June series, we focused there more on marine corrosion, and we all agreed that the concept of corrosion in the marine environment was something we would definitely anticipate. But what about what we call normal water or fresh water? So today I'm delighted that Webb is joining us, and we're going to just explore a little bit of this concept of water and how it can be contaminated. So Neil, thank you for joining us, and let's have a look at water, shall we?
Yeah, thanks, Vanessa. The concept of seawater, of course, being corrosive is common. We think of rusty ships, we think of the problems of atmospheric corrosion near the coast where you get windborne spray from the sea, which brings in chlorides in particular, but salts in general. And we all know that when you go to the beach, at the end of the day, if you were to lick your skin, it would be salty from the sea spray. We can't drink seawater. It's got too much salt in it. And so we expect things to corrode when they're at the coast or associated with the marine industry, be it, actually on board ship or marine infrastructure like harbors and jetties and offshore platforms and all the rest of it. And so therefore, we take precautions against it with cathodic protection and coatings and material selection and so on. And for those of us who don't normally live next to the coast, we tend to think of our environment as being non-corrosive. And the water that is associated with our life is just there. It's not corrosive. And yet I remember being startled by a bit of an unfortunate experience a few months back, based in Johannesburg, and a piece of material that had been machined, so it had a nice clean steel surface, inadvertently got left out in the rain. And the next morning it was covered in rust. So we need to realize that water is associated with corrosion, no matter where we are. And perhaps it is the severity, the type, the extent of corrosion that we need to delve into in this series, and today setting the scene. And so we're just going to introduce some concepts that are associated with water and what it's made up of, and why we need to be cognizant of the different situations that can occur which cause corrosion.
Just going back to your analogy with the seawater, Neil, when we think of fresh water, we know we can't drink salty water, and we say, well, fresh water isn't salty. And so that does tend to lead us into the temptation of thinking that water is not corrosive. And yet, as you rightly say, it is corrosive. But if we even look at pure water, let's just talk about how we can think of the purest water we can imagine, whether or not that is corrosive.
Well, there's all sorts of hype around drinking distilled water. And yet, drinking distilled water is probably a very unhealthy thing to do, because distilled water or deionized water has had all the salts taken out of it, either by distillation or by ion exchange. And the water itself then is hungry, and hungry water will attack anything. And so we see in our power stations, for example, that they go to extreme lengths to protect the infrastructure, the storage vessels and so on, associated with the demineralized water that is used for boilers as boiler feed water. And this hungry water, if you put that into your body, it's going to dissolve your bones. Now, there may be people out there who disagree with that point of view, but, so you drink deionized water or purified water or whatever you want to call it, and then you go and take mineral supplements to counteract it. And that's just weird.
The interesting thing about water is that water is critical in our corrosion reaction. In fact, all of the corrosion that we talk about is electrochemical in nature, and we need something to carry the ionic current, and that is water. So water, by definition, must be involved in the corrosion reaction.
Yes, absolutely. I mean, we do get corrosion reactions that occur at high temperature in dry atmospheres. There's high temperature oxidation and sulfidation and chemical reactions that take place. But the majority of our corrosion issues are related to water. We need water for the electrochemical process to occur. And so if there's no water, there's no corrosion. We use dehumidification, for example, which we've spoken about in our atmospheric corrosion series. You reduce the humidity to less than 40%, and you don't get atmospheric corrosion. So the presence of water is necessary for our corrosion reactions.
So if we're going to talk about waters, maybe I can call them natural waters. Let's look at what makes them corrosive.
Well, all water is natural. It occurs in nature. But, of course, there's all sorts of waters. Here's some adjectives. You get fresh water, you get hard water, you get soft water, you get brackish water, you get sparkling water, mineral water, sweet water, processed water, purified water, treated water, distilled water, deionized water, stagnant water, balanced water, boiler water, cooking water, chilled water, salt water. I mean, what more do you want?
All right, let's talk about non-processed water, water that falls from the sky into the ground, into our space. Let's use that as our definition of natural. And if that is natural, then we've mentioned that those waters can be corrosive. But I think it's worth talking now, if we treat that water, we're calling water natural, all water is natural. What is potable water? Let's get that definition out the way.
Yeah, so potable water is a very interesting terminology because we often see in specifications related to preparation of surfaces for the application of coatings that the surface needs to be washed with potable water. Now, that's actually a very dangerous statement because potable water means that it is safe for human consumption or cooking purposes. When you actually look at the standard for potable water, it's quite amazing the level of dissolved salts that is allowed in potable water for human consumption. And when you think about potable water, my personal experience is, for example, is in the UK, they have a lot of chalk in their ground. And so generally their water is very hard. In other words, it's got a very high calcium level, and it's fantastic for hard bones and strong nails and everything else. But it's by no means a water that is low in salts. It's actually got a very high salt loading. Just so happens that that salt is calcium carbonate. We need to remember the broad definition of a salt is a combination of an acid and a base to form, you get a salt. So we tend to think of salt as sodium chloride, but calcium carbonate is a salt. Yeah. It's a hard salt, sure.
And it doesn't taste as salty as marine water.
No, right.
Neil, there are so many water options we can consider and way too little time to look at them all. But I think it's really worth looking back at the basic building blocks of water. Water comprises 2 hydrogen atoms, 1 oxygen atom. And let's start right there and think a little bit about what this water is, and then maybe we can understand it and how it works a little bit more.
Sure. Many of you may have seen this parody that was doing the rounds on the internet where somebody took on the Minister of Health or whatever, I think it was in a district or a state or something like that, about this compound called dihydrogen monoxide. And they say, here's just a couple of quotes from it. If anybody's interested, just go and look up dihydrogen monoxide on the internet and have a look at the full story. But here's some things that come out. It is also known as hydroxyl acid and is the major component of acid rain. It contributes to the greenhouse effect. It may cause severe burns. It contributes to the erosion of our natural resources and landscape. It accelerates corrosion and the rusting of many metals. So what's this horrible stuff? You know, we've got to do something about it. They actually managed to get the parliamentarians to put a motion before the assembly or whatever it was to ban or outlaw this product called dihydrogen monoxide.
And then they would have died for lack of water.
Yeah,
That's
yeah,
actually
right.
terrifying. It is terrifying, and a little bit of knowledge can be a dangerous thing. But because of its chemical structure and layout, of course, water can be, in many ways, all things to all people. And when we think of it as possibly being called hydroxyl acid, we then start to panic about whether we can drink it at all. And of course, that needs to sort of shake us a little bit to take stock and behave ourselves and think about it a little bit more logically. Because of course we can and we do drink water. And I'm one of the first to put my hand up and take water over almost any other drink. So Neil, what would make water suitable for drinking?
Well, on the subject of acid, there are some very well-known soft drink brands around that really are acid, such that if you were to take your teeth out and leave them in that drink overnight, your teeth would dissolve. The fact of whether it's acid or not is neither here nor there. But what makes our hydroxyl acid balanced or neutral is the fact that there is an equal concentration of acid and alkali or base. So there's equal concentrations of hydrogen on the acid side, hydroxide on the basic side or alkaline side, and we have what is called a neutral pH. So pH is a measure of the acidity of water, and it is one of the primary parameters that we can measure to determine whether or not we have corrosion. Because if water is balanced and neutral, it has pH 7. If it is at the pH of 4, which is doesn't sound much difference between 7 and 4, but it's a logarithmic scale. So it's 1,000 times more acid. And each pH number is a factor of 10 times in terms of acidity or alkalinity. So the acid waters cause corrosion. The alkaline waters help to actually prevent corrosion because they form stable oxide films. And at high pH, such as when we see steel in concrete, for example, steel in concrete is very high pH and the steel doesn't corrode unless there are other factors.
So there are many ways actually that we can look at water and determine its corrosivity. And pH is definitely one of them because that's an indication of the acid. And we know that acids are corrosive. But let's just have a quick look at some of the other ways that we can measure how a water is corrosive.
Well, one of the most common ones is what is called the corrosion or scaling index, generally known as either the Langelier or Reisner index. And it is a calculation that's done based on the carbonate balance of the water. So it looks at calcium carbonate, magnesium carbonates, bicarbonates, and so on. The parameter measures what is called the pH of saturation. In other words, the pH at which the water would be saturated with calcium carbonate, bearing in mind that most soluble salts have a concentration at which they will no longer dissolve, maximum concentration. So that's called the saturation. So the pH of saturation is the pH at which the water would be saturated with the calcium carbonate mix. And they compare that pH of saturation, which is a calculated number, against the actual pH, which is a measured number. And if the pH is more acid than the pH of saturation, you have water that will tend to dissolve scale. And if the pH is more alkaline than the pH of saturation, the water will tend to deposit scale. There was a situation at one stage where they were treating the mine dump in and around Johannesburg, and they were using water to hydro-demolish the dumps, pumping this water slurry back through to the treatment plant, and that water would then dissolve some of the salts from the mine dump operation. That water would then get returned back to the dump, to be reused again. So this water was going round and round and round and picking up salts all the time from the dumps, and it was precipitating out in the pipes and so on. And some of those pipes went from being maybe 150, 200 millimeter diameter, and they closed down to the point where they could no longer pump. And it was actually, I've got a sample of one of those scales. It was centimeters thick and actually very beautiful. It was a sedimentary rock geology formation compressed into a very short time space. And you had these beautiful layers of different salts that were all crystallized out inside the pipes.
It's an interesting thing because, I mean, the scaling of a pipe diminishes the volume of water that it can carry. But by the same token, if your water is a scaling water, it's not corroding. And that's also the balance that you may want to go to, because obviously if your water isn't able to precipitate the salts, it then is more likely to be able to dissolve salts. And we can't only consider the carbonate balance, Neil. We need to also consider some of the other salts. We know chlorides, we know sulfates can also be a challenge in terms of their presence in a water causing corrosion.
Yes, just to harp back on that question of scaling, decades ago, one of the major water utilities changed from using a lime-based water treatment to, I can't remember what the correct term was, a different water treatment, which reduced the scaling effect of the water, which was great in terms of scale buildup. But they landed up with an increase in the level of internal corrosion, and leaks which had been blocked by scale became apparent. Probably something or other that they used. Maybe one of the, I don't remember it offhand. But going back to your question about sulfates and chlorides, that is very, very important, particularly in the mining industry, where you've got sulfide rocks being mined, and you get very high sulfate chloride levels. And so there's a corrosivity index that you need to consider in terms of the chloride and sulfate level, where the chlorides and sulfates are compared to the total alkalinity of the water. And you can land up with a water that is scaling in terms of the calcium balance, the carbonate balance, but highly corrosive in terms of the chlorides and sulfate balance. So
and then you lose on all fronts.
Yeah, and the other aspect of sulfates in particular is that high sulfate waters, if you then land up with stagnant water situations, are a breeding ground for bacteria, for the anaerobic bacteria.
That's true. And we'll drop the link into our discussion with Reza in the middle of last year when we spoke about microbial-induced corrosion and the impact of anaerobic bacteria. It was a very interesting discussion. But Neil, one of the challenges that you've just raised, or another thought that you've just raised in my mind, is it's all very well to reduce the sulfides and be fearful of these anaerobic conditions because of sulfate-reducing bacteria. But when we've been chatting previously, if we reduce the oxygen, so creating an anaerobic environment, that's actually beneficial from a corrosion perspective. So yet another balance that's a challenge.
No, absolutely. And I mean, Amintech did a lot of work in the 80s in particular on evaluating the causes of corrosion or the severity of corrosion. I mean, we in the mining industry. And one of the major factors that came out of that study, which was done primarily by one of our good friends, John McEwen, was that dissolved oxygen actually was one of the primary factors in determining the corrosion rate or the corrosivity of mine waters. So you could have these waters with thousands of parts per million of chlorides and sulfates that were relatively non-corrosive because of the lack of oxygen.
And I think that just leads to the sort of conclusion that actually when we're looking at waters and the consideration of corrosion as a result of waters, it's not just one parameter. It would be so easy if it was. Okay. But you need to get this almost tightrope balancing effect of considering all of the various components, the conductivity, the scaling tendency, the various salts that are in the water, the pH, the oxygen, and I'm sure many more. I'm not a water chemist by a long shot. and taking all of those into account to determine whether your water is shall we deem it a safe water, or whether corrosion is going to be a challenge.
It's not only about the actual composition of the water. There have been a number of situations where, we have a vast network of water pipelines and storage facilities in and around Gauteng, and obviously elsewhere. And this water gets treated and pumped and stored. And there have been a number of cases where I've been involved in condition assessments of reservoirs, where you go into the reservoir internal and you find that the flow characteristics in the reservoir are such that there's a dead space. And so the water does not get refreshed in that reservoir. And lo and behold, you land up with bacterial corrosion in the dead space, in what is otherwise a completely non-corrosive environment. We also had a situation happen in Namibia, where they put in a new pipeline network to provide water, potable water, to villages and areas that previously didn't have water. They used galvanized steel pipe, which was absolutely fine for the water conditions. They hydro tested it on completion of construction using borehole water, and then didn't drain it. So this water now, instead of flowing through it, sat stagnant. Before they were able to commission it, it was full of holes because they didn't think about the bugs.
Yes. Wow. So I think just to tie up today, when we're starting to talk about water, and this little mini series will be focusing on water and contamination and the impact of those contaminations. I think it's been helpful just to remind ourselves that water is in and of itself a medium of where corrosion occurs, and we can consider that all waters are corrosive or could be corrosive. So thank you, Neil, for helping us explore that a little bit. And also our brief foray into the acidity of water actually opens the door beautifully for our discussion tomorrow with Professor Anthony Turton. And I really encourage everyone to join us. Prof. Turton is the world authority on acid mine drainage. Again, here in Gauteng, it's become synonymous with scary thoughts and a whole lot of people promising magic cures. But I have absolutely no doubt that tomorrow we're going to have a really illuminating conversation with Prof. Turton as we discuss acid mine drainage, what it is, what it isn't, and how it is still a problem, even though it's no longer quite as newsworthy as it once was. So thank you, Neil, for helping us to set the stage. Thank you.